Hello and welcome to York Observatory's monthly Teletube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. We are broadcasting live from the Alan I. Carswell Observatory, located at York University in Toronto, Ontario, Canada. York YouTube broadcasts every last Friday of the month at 7:30 p.m. local Toronto time here on our YouTube channel at York U Observatory. For any questions or comments you have of our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on Twitter with the handle @York Observatory, Instagram @York U Observatory, and Facebook @Alan I. Carswell Obs. I would like to inform you about the opening and call for applications for the Summer of 2024 Astronomer in Residence program. This program is a collaboration of the Alan I. Carswell Observatory with Killarney Provincial Park to host astronomers in the certified dark sky site of Killarney to lead in-person presentations and shows using the park's observatory. To learn more about the program and its requirements and the application process, please visit our website at yorku.ca/science/observatory/air. Good evening, everyone. I am Zena, and I will be one of your hosts this evening, along with Maheen, Noor, and Pouria. This evening, we are joined by a very special guest, Professor Alireza Rafiee, who will be talking to us all about black holes and galaxies. Before we begin with our show tonight, I would also like to mention that the observatory at York campus in Toronto and we would like to welcome you all to our show and to acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional treaty territory of many Indigenous nations. The area known as Takaranto has been caretaken by the Anishinaabe Nation, the Haudenosaunee Confederacy, the Huron-Wendat, and the Métis, and it is now home to many Indigenous peoples. We acknowledge the current treaty holders, the Mississaugas of the Credit First Nation. Our stargazing and astronomical efforts join the long history and current practices of astronomy for this land. The observatory looks forward to continuing to learn and revitalizing our knowledge in this area. I will now hand it over to Noor to get us started with What's Up in the Sky.
Welcome, everyone, to our What's Up in the Sky segment. As we gather tonight in Toronto, let's dive into the celestial sights available to us this week. Tonight, our moon is enchanting in the waning crescent phase, which will paint a delicate crescent in the pre-dawn sky, providing a perfectly dimly lit canvas that enhances the visibility of both stars and planets. The constellation Leo is high in the southern sky, with its bright star, Regulus, easy to spot. This is a perfect time to view the galaxies located within Leo, including the Leo triplet, a small group of galaxies that can be seen through a moderate telescope. For those with telescopes, the Virgo cluster of galaxies is also well positioned for viewing. This cluster contains over 1,000 galaxies and is a highlight for anyone interested in deep sky objects. Looking north, the Big Dipper is predominantly displayed, guiding us to the North Star Polaris. This is a great opportunity to teach younger viewers how to find true north using the sky. Not to be outshone, but Jupiter, the mighty king of planets, will also make a grand appearance in the morning sky. Arm yourself with a pair of binoculars or a small telescope to catch a glimpse of Jupiter's famous Galilean moons, arrayed majestically like a string of pearls across the heavens. As we enjoy the night from our vantage point in Toronto, remember to dress warmly and give your eyes time to adjust to the darkness. Light pollution can be a challenge, so if you have the opportunity, find a spot away from city lights to really appreciate the fainter galaxies and star clusters. Now, I want to give you guys a few stargazing tips to make the most of your experience. 1. Early bird special. Set your alarms early to catch the constellations and planets to their prime viewing time before sunrise. And 2. Dress for success. It might be chilly, so wear something warm and give your eyes at least 20 minutes to adjust to the dark for the optimal stargazing experience. So, mark your calendars, set your alarms, and prepare for a celestial journey that brings you the mysteries of the universe right to your doorstep. After our session tonight, step outside and breathe in the fresh air, and let the cosmos enchant and inspire you. Enjoy the spectacle and let your imagination soar among the stars. I will now hand it over to Pouria for the speaker's introduction. Thank you.
Ladies and gentlemen, it is an honor that our guest for tonight is Dr. Alireza Rafiee. Professor Rafiee has a wealth of expertise spanning theoretical and observational astronomy as well as cosmology. He holds a PhD in astrophysics from York University, specializing in the enigmatic realm of supermassive black holes. Prior to joining York University, he served as a postdoctoral fellow at Towson University, Baltimore, delving into the intricacies of galaxy clustering at large redshifts. Since 2014, he held teaching appointments at York University as well as Toronto Metropolitan University since 2018. His instructional repertoire includes captivating subjects such as astronomy, exploring the solar system, and delving into the mysteries of cosmology. With an unwavering dedication to education and research, Professor Rafie's tonight talk is about galaxies and black holes.
Okay, good evening, everyone. Thank you, Pouria, and thank you, Zena. Welcome to tonight's discussion about black holes in galaxies. So my goal for tonight is to talk about, of course, about black holes in galaxies, which, when you think about it, they look irrelevant at the start. So I'll try my best to define what a black hole is, how many different kind of black holes we have, what a galaxy is, and how the connection between black hole and galaxies are. Of course, we want to know how we can make a black hole and how we can discover a black hole, and hopefully how to measure the mass of the black hole. I'll try my best not or to use as minimum mathematics as required. So I guess at the end of the night, you will be happy with just hearing a lot of stories about what happened and who discovered and what we know about black holes and galaxies. Before I start, let me tell you a story about who basically came up with the idea, with the name of black holes. Before John Archibald Wheeler, people didn't call black holes black hole. They used to be called dark stars or black stars. So he basically popularized the term black holes in mid-20th century. But people knew about these kind of objects for a very long time. Indeed, the first basically question or address to this problem goes back to around 1783, when John Michell, an English natural philosopher, a clergyman, he published a paper about a hypothetical object which is so huge and so large, which even based on Newtonian gravity, nothing, not even light, can escape from it, and it has to be dark. So he called it a dark star. But since then, and especially after 1920 publications of Albert Einstein's general relativity, gave us a better framework to talk about black holes and to understand them. Which brings us to this question: what is a black hole, right? Now, before I tell you what a black hole is, I want you to think about this question. What is an electron? Well, everybody knows what an electron is, right? A very abstract particle around an atom. We understand it from electricity, capacitors, lightning, frictions, all these things, claims that these are related to the properties of the electrons. And so how electron interacts with the world tells us something about the electron. So we understand an electron as a fundamental particle, rather very abstract object, with some certain mass, some certain charge, some certain spin, and some certain specific interaction with other objects in the universe. It uses electric force, magnetic force, gravitational force to communicate with the rest of the world. So you might say electron is something with a mass, charge, spin, and interacts with the world with gravity, electric, and magnetic force. Well, I would say black hole is almost the same, maybe even simpler as an electron. It's a strange perspective, but when you think about it, a black hole is, again, an abstract object, very fundamental. And when you think about it, is a very simple celestial object. It has mass, it has charge, and a spin. And perhaps it interacts with the rest of the world with gravity, electric field, and magnetic force. Oh, I can even make it even more simple than an electron. We know that the overall charge, electric charge of a black hole is almost zero. So there's no charge to think about it. So there's no electric interaction in a large scale. And also the spin of a black hole is a function of the mass of the black hole. So at the end of the day, you will have only the mass and a gravitational interaction with the rest of the world. So you have an object, abstract, and if you know the mass of that object, then you know everything about it. It's awesome, right? It's very simple. It can't be even easier than that. I know you think it's cheating, right? Because we have so much trouble understanding what's happening inside a black hole. But when you think about it, you don't know anything about inside electron either. But you're not bothered with that question. Now, the reason we are interested about what is happening inside a black hole is because you have a possibility to fall into a black hole. And so you want to know what would happen or what is inside a black hole. But if I have to be honest, and we have to, we don't know anything about inside the black hole. And we cannot know anything, at least for a while, until we find a framework, a theory, which is able to describe what is happening inside a black hole. Some people have tried the suggestions, or there are many, many suggestions. You can say black hole is very small, so you need quantum mechanics to work there. Also, you can say the black hole is very massive, so the gravity has to work there. So general relativity and quantum mechanics, if you put them together and mix them, perhaps you should be able to find a new theory to describe what is happening inside a black hole. But we don't have such theory. And that's the problem. There is a boundary around a black hole. We call it event horizon, that blocks our view, our understanding about what is happening inside the black hole. So some people like to define a black hole as a region of a space-time, not space and not time, together, space-time, where the gravity is so strong that nothing, including light or any electromagnetic wave, radio, gamma ray, X-ray, doesn't matter which one, nothing can escape from it. Or you can say nothing has enough energy to escape from it, and it's technically impossible to do so. So the black hole basically is a one-way out of this universe. We have to remember that the black hole do not suck on the matter. They're not space vac. They're not space vacuum cleaner. If you aim at them, it would be extremely hard actually to fall into a black hole. If you are moving, and to some degree you can say everything in the universe is moving, there is nothing stationary in the universe, with respect to a new coordinate system, you are a moving object. And so eventually, when you want to fall into a black hole, you have to lose angular momentum with respect to that coordinate system. And that is a very hard thing to do. So beside that, the black holes are extremely small. So long story short, if we know the mass of the black hole, then you know everything about it. Okay? Now, the other thing is, the reason we don't know what is happening inside the black hole is that it's not because we have not tried to understand what is happening inside it. The frameworks that we know at the moment are not powerful enough to explain what happens inside it. Or you might say, by studying the black hole, we might actually find reasons or ways to find this ultimate theory of quantum gravity, which can help us to understand a black hole. So it's a two-sided coin, maybe, if you like. Well, for the last 90 years, people have tried significantly to understand this quantum gravity. Some people even thought out of the box. Like, for example, string theories have tried to completely change the game. Instead of thinking about particles in the universe, they have tried to explain everything with very thin strings of energy. And they have tried to explain electrons and protons and, of course, black holes. Now, unfortunately, there is no success in any of these models, and we still have to wait. Okay, so that's for defining what a black hole is. It's a very abstract object, very simple. Only one parameter is needed to define it. Okay, now let's just go and define how many different types of black holes we have. I would say we have very small, big, and very big black holes. Of course, that is not very helpful, right? We need some numbers to put into the perspective. If a black hole mass is smaller than Moon, and what you do is, and the reason we do it based on what is around us is some kind of anthropomorphic approach, right? Humans are important in this picture. We want to understand them based on our own scale, and Moon is one of the smallest celestial objects around us. So if you take the mass of the Moon and shrink it to a size of 0.1 millimeter, which is almost like a dust particle, then you will have a very, very small black hole. Okay, now it's a good name. I like this very small black hole, but some people like to call it different, like micro black holes, quantum black holes, or primordial black holes, depending on how they describe it and how they use it. We'll talk about it, how they are formed later. So this first kind is very tiny micro black holes, they're very low mass black holes, smaller than Moon, and very tiny in size. The second kinds are more typical, things which are the size of the mass of the Sun, the largest stellar or celestial object around us. You take one solar mass or 10 solar mass and you shrink it into a size of a few kilometers of volume of space. That creates a stellar black hole. These black holes are very common, and so we can actually make sense of them. We can understand them. There's a range for them. Stars cannot be smaller than 10% of the Sun's mass, and they cannot be larger than 100 times of the Sun, approximately. Maybe 150 solar mass, you might find one or two stars of that size. But in general, most of the stars are within that range, okay, between 10% to 100, 150 times of the Sun. So you can have black holes with the size of around 3 solar masses to around maybe 40 solar masses. That's the range of the stellar black holes. You can also have black holes. We call them intermediate black hole masses, intermediate mass black holes. These are black holes, hypothetical black holes, suggested basically to explain how some structures exist in the universe. They can have a mass between hundreds of solar masses to hundreds of thousands of solar masses. Typically, you can find them within small galaxies or clusters of stars, globular clusters of stars. The size of these black holes are, again, in average, the size of the planet Earth, or at maximum, they can be the size of the moon orbit. Pretty small when you think about it. We can also have the largest kind of the black hole. We call them supermassive black holes. These are gigantic black holes, sometimes tens of billions of solar masses. But they can start from millions of solar masses up to maybe tens of billions of solar masses. When you squeeze this mass into a volume of space, they can occupy in a space as large as maybe the solar system, maybe the orbit of the Earth, up to as large as the entire solar system. So that's the size and the range of the mass we are talking about. Now, there is a practical limit for supermassive black holes. We have not seen anything bigger than 10, 15 billion solar masses yet. And it seems that they are related to the size of the galaxies as well. Okay, now this black hole idea, it was first calculated by Karl Schwarzschild. He was a mathematician, a German mathematician, who solved Einstein's general relativity field equations in 1915, actually. Assuming that the entire mass of a solar mass or sun is in one point. And then he basically calculated the size of the event horizon. Okay, now the question is, how do we make these black holes, right? I mean, different size of the black holes, and you can make them in different ways. So the most common one, a realistic one, are the stellar black holes. If you have a star with a mass which is quite large, maybe 15 or 18 solar masses. Now, typically stars are burning hydrogen in the core. And this hydrogen fusion is important to keep the star stable. You see, there's a fight between gravity and the gas pressure. The gravity wants to collapse the entire mass into one single point called singularity. If there is nothing against it, then the gravity wins the battle, and the entire object, whatever it is, it's going to contract into one single mathematical point. Now, in a normal planet, you have, in a normal solid objects, you have electrons. These electrons have basically properties which allows them to create a pressure against the gravity. So a solid is not contracting into a black hole. A planet is not shrinking into a black hole because you have an uncertainty principle and Pauli principle to prevent the planet from contraction. There is a pressure created by these electrons to stop the gravity. For the gaseous object like stars, you don't have these electron pressures. Rather, you have electrons moving with some velocities. You fuse hydrogen in the core that generates energy. The energy causes the electrons and the particles to move very rapidly. That creates a gas pressure, and the gas pressure prevents the star from collapsing. Technically, stops the gravity. Now, if the star is 18 solar masses, about 10 to 20% of that star is capable of burning, fusing to helium to generate energy in the core. And so that can prevent a star from collapsing as long as the star is burning hydrogen. But stars have a finite amount of hydrogen. Fuel runs out, and eventually a new fuel may actually kicks in. For example, helium, after hydrogen burning is gone, helium starts burning. If the star is big enough, then carbon can burn, oxygen can burn, and this continues until eventually the core is piled up with iron. Now, the reason iron is important because you cannot fuse iron to generate energy for a star. You can fuse iron to create heavier elements, but this is not an exothermic process. It's endothermic, which means it's not useful for the star. It cannot create more pressure against the gravity. So when star reaches that point where you have a core made of iron, then the gravity continues collapsing the core, and there is nothing to stop the gravity. Now, initially, electrons eventually reach each other's and create this degeneracy pressure, the electron degeneracy pressure. But because the core is now heavy, when you have an 18 solar mass star, the core is maybe approximately 3 solar masses now. The mass is so huge, electrons cannot hold against it. And so the electrons mix with the protons in the core and create neutrons. Now, this process changes the size of the core immediately. In a very short amount of time, a fraction of a second, the core of the star shrinks to a 100,000 times smaller size, releases a huge amount of energy, and that energy goes out and explodes the outer layers of the star. Now, this is referred to as supernova explosions. And when the core of that star is more than 3 solar masses, even the neutron degeneracy pressure is not enough to stop the gravity. And so that central part contracts even more and eventually crosses the event horizon. When it becomes smaller than the event horizon, then it disappears from the view. It becomes black. So there's 2 concepts here when we talk about the black holes. One is the singularity, which is a hypothetical point at the center of the mass where, because of the gravitational collapse, the entire mass is supposed to accumulate in that point, a zero radius, infinite density concept. We can never see singularities, but there is a hypothetical area around the black hole in which, if you are inside that hypothetical surface, the event horizon, then the speed you need to escape from that object is higher than the speed of light, and so you cannot escape from it. That's why they're called black hole. They are black because they neither emit nor reflect light. And it's definitely a hole in a 3-dimensional space. You can enter that black hole from every direction. It's not like one of these images you see, a 2-dimensional images. It's more like a 3-dimensional hole. The size of this event horizon can be estimated only as a function of mass. Of course, if the black hole is stationary and symmetrical, it's not rotating. This was calculated by Carl Schwarzschild, and it is approximately, if you measure the mass of the black hole in units of solar mass, it's about 3 kilometers times the mass of the black hole. So if you have 1 solar mass black hole, then the radius of that black hole, the event horizon, is 3 kilometers. It's a very tiny object when you think about it. If you have a 10 solar mass black hole, then the size of this black hole would be 30 kilometers, almost the size of the Great Toronto Area. Okay, but the mass is huge, and so the gravity causes the space-time around this black hole to be significantly curved, which, as a result, can affect whatever is approaching it or whatever is orbiting around. And especially it can affect the light. And so what you see in this image is affected by the gravity of the black hole around the event horizon. So the event horizon marks technically the point of no return. Anything falls into the black hole, anything crosses that event horizon, doesn't matter from which direction, it enters the hole and it never returns. Now, what happens inside a black hole, it's not my interest. Nobody knows what happens inside a black hole. We only hypothesize about what is happening inside the black hole. You can never see the singularity of the black hole. Some people have hypothesized that the space gets so curved, eventually it is pierced through the fabric of space-time from the other side, and the matter eventually flow out of that side, creates a white hole. But again, this is only a hypothetical idea. We don't have any proof, and we have not seen any white hole in our observable universe. And unless we have a quantum gravity theory, we cannot talk about what is inside a black hole. So this idea of event horizon, the surface defined by the Schwarzschild radius, was technically defined in 1958, almost mid-20th century. So stellar black holes are quite easy to form, and there are some good evidences for them. Technically, we can detect them, and we have discovered many of them. What is hard to detect are the other kinds. For example, micro black holes or mini black holes, or if you like, call them primordial black holes. These are very small. If you take the mass of the moon and shrink it into a 0.1 millimeter size, you will have a black hole of that kind. Okay, so before we go even further, I have to first declare that these black holes have not been detected. The existence of these hypothetical black holes are only predicted to be the result of some random fluctuations in the density of the universe at the moment of Big Bang. Before Big Bang, we perhaps had a quantum vacuum. And according to the laws of quantum field or quantum physics, the quantum vacuum is full of energy and energy fields. The vacuum energy density then fluctuates, and in a short or maybe a very short amount of time, according to Heisenberg principle, randomly the space and time generates regions with mass, matters and antimatters. This happens perhaps during the first 10 to the power of minus 35 seconds of when the universe came to exist. Some of these large fluctuations in density, perhaps they condense into very small regions of space. And when the universe was expanding through this rapid expansions of the inflationary period, then these masses were trapped into these very small regions and formed these micro black holes. As you can guess, and as I mentioned before, these are called primordial black holes, and they are very hypothetical. We have not detected any of them yet. Now, there are two reasons for not being able to detect them. One, they are extremely small. Imagine it's quite hard actually to see a dust particle with eyes. Now, imagine if you have black holes of that size lurking around in the space, far away from you. I mean, it would be extremely hard to detect. Yes, they might distort the light of the stars and the galaxies, but the noise, the level of noise is still very high, and we may not be able to see that kind of distortion. But the second reason for them is A while ago, in around 1966, Zaluj and Novikov, and later Stephen Hawking, they predicted that these objects, these black holes, may not actually be 100% dark. They may actually radiate. These are referred to as the Hawking radiations. And so these radiation allow a black hole to evaporate. And the time these black holes can survive is proportional to the mass of the black hole to the power of 3. Which means the smaller are the black holes, the faster they evaporate. Now, why these evaporation and radiation exist is a little complicated, but if I have to put it in a simple language, when you have a black hole, then the curvature of the space and time around the black hole is extremely curved, and the energy density of the space-time is extremely high. Now, according to quantum mechanics, the vacuum is fluctuating. And when you increase the energy of the space and time, then you give the vacuum this possibility to create particles and antiparticles in general. But when the space and time is so curved, if it happens that you generate, or the vacuum generates a matter and antimatter, an electron and a positron, very close to the event horizon, then the contraction of space and time will create a separation, a real separation between the particles and antiparticles, the matter and antimatter. Now, assume that the matter falls into the black hole, it's closer to the black hole, and it falls into the black hole. The antimatter is now separated from the matter, and so it becomes a real particle. Now, the vacuum, according to quantum mechanics, is able to produce these virtual particles continuously, but when they are very close to the edge of the black hole, then suddenly these virtual particles become a real particle. And now this antiparticle left behind can interact with another electron and annihilate themselves, and then eventually creates two beams of light, where the light can escape from the black hole, because it's outside, because it's generated outside the event horizon. And so Hawking explains this evaporation through this process of pair productions of matter-antimatter very close to the event horizon. So in that scenario, black holes evaporate, but it takes time for them. If you have a black hole the size of moon, it takes some hundreds of billions of years to evaporate. But if you have a black hole the size of the asteroid Bennu, then it takes less than the age of event solar system, like less than 4 billion years to evaporate. And so all these primordial black holes, perhaps if they are smaller than asteroid Bennu, let's say, have already been disappeared. There's no chance for us to observe them. And the rest of them are perhaps quite hard to detect. Okay, that's for the primordial black holes. But what about intermediate-sized black holes? These black holes, if you remember, are black holes with a mass between 100 to maybe 100,000 solar masses, with a moderately small size, planet Earth or the orbit of the moon. They are hypothesized to be found in globular clusters of stars. You can see one image here, and maybe small luminous galaxies. But unfortunately, we don't have any proof for them yet. There are some claims detecting these intermediate black holes within the globular clusters, but they are yet to be confirmed. Well, how do we generate these kind of black holes? We don't have any straightforward mechanism to generate a black hole of this size. There is a limit for the size of the stars. When the stars get bigger than 100, 150 solar masses, the amount of radiation which comes out of the star prevents the star to get bigger. So there is an upper limit for the size of the star. But there's no limit for collision between the stars. And so some people have claimed that maybe you can generate these intermediate black holes by merging, first of all, the black holes, or merging the stars. In the middle of these globular clusters, the density of the stars is pretty high. And the probability for them to collide is higher than a normal environment like around the sun. And so if stars interact and eventually collide, they can perhaps create these intermediate black holes. Some others have claimed that maybe they have been formed at the beginning of the time during the Big Bang. So they might be even primordial black holes. But again, there is no easy, simple mechanism to explain how they should be formed. So they remain hypothetical, okay? Which brings us to perhaps the most interesting one, the supermassive black holes, the one which are at the center of most of the black holes. Now, these black holes are quite large, first of all. Most of the galaxies have at least one. There are some evidences for some observations with for the galaxies with more than one supermassive black holes. They accrete matter. They are lurking in the middle, at the center, in the middle of the galaxy, and within the center of the galaxy, typically the density of the stars and gas is higher. And so when matter is falling into the black hole, usually they form these flattened structures. We refer to them as accretion disk. Accreting matter into the black hole will allow the black hole to grow in size, but also it creates radiation for the black hole. So you can have a black hole which is not fed by gas and stars, and so we can call them inactive black holes. Normal galaxies typically have these kind of black holes. And then you can have black holes which are fed by the stars and the gas, and they have a significant accretion disk process around them. These are called active black holes. And the galaxy itself is called active galactic nuclei in general. Now, these active galactic nuclei are extremely bright. They are so bright, we can even see them at the edge of the universe. Black holes, quasars, or AGNs at redshift 10 has been observed by astronomers, and the mass of the black hole has been measured through some of these techniques that we are going to talk about. So these supermassive black holes are at the center of the galaxies. They typically have, in the case of active galactic nuclei, they have accretion disk formed around the black hole. And then around these accretion disks, typically you have regions of space where the matter, gas, dust, molecules, stars are basically lurking around and rotating around the black holes. Now, if you are lucky and you look through these jets of materials which are ejected out of the surrounding of the event horizon, then what you would see is an incredibly bright point sources called blazar. But if you look at angle, you might be able to see the accretion disk, partially or fully. And so you will see an extremely bright region, bright point in the sky, which varies with time, usually referred to as quasars or quasi-stellar object. Some galaxies, spiral or even elliptical, close by, within maybe a few billion light years, also have active galactic nuclei. But when you look at them from different direction, you will see them in different shape. Which brings me to this point to define what a galaxy is. Well, our universe is made of matter and energy. These are the content of the universe. 70% of the universe is something which causes the universe to expand. Space and time is expanding because of that 70% negative gravity-like things. We call it dark energy. It doesn't radiate. We cannot observe it directly. The only evidence we have for this kind of things in the universe is the rapid expansion of the universe we live on. 25% of the universe is similar to normal mass. It has a positive gravity, attractive gravity, but it's still dark and we cannot see it. So we call it dark matter. Only 5% of the universe is made of normal matter, kind like you and me. Out of that 5%, only about 0.5% of it forms stars and radiates. 4.5% is gas and some other things. Everything else, planets, asteroids, and neutrinos and everything else. Okay, but we can only see the stars. Some of the gases can be also visible in some radio bands, but at least you can clearly say that they are not radiating, and if they are galaxies. So a galaxy then is defined as a collection of these stars, the gases, and everything else, and particularly a lot of dark matters. They all together in one entity, binding together by gravity, the mass, the positive attraction between the mass. And they are typically huge. There is a vast empty space between the galaxies and also between the stars inside a galaxy. So our Milky Way is a galaxy. It has about a size of about 100,000 light years with a thickness of about 1,000 light years. It's a disk pattern. It's a disk galaxy with some arms. So it's a spiral galaxy. But it's mostly empty space. The separation between the stars is pretty far. I mean, the density of the stars is almost like 0.01 star per cubic light year. The nearest star to us is about 5 light years away from us, right? So there's nothing. There's just only a little gas between us and the nearest star. So there's a huge empty space between the stars. Now, these galaxies also are far away from each other, and there's a huge empty space between them. And they come in a variety of different shapes. They can be very symmetrical, with a little gas, a lot of dark matter, large size or a small size. We call them elliptical galaxies. They can be rotating. The stars within the galaxy might be rotating in the same direction, forming a disk pattern structure. We call it the spiral galaxies. They usually have some 10–20% gas, but the rest is dark matter and the stars. They can also have irregular shape, no shape at all, mostly made of gas and newly born stars. They can have very small size to moderately small size, and they all can be active or inactive. They can have a black hole growing in them, or they can have a black hole which is dormant and not growing. So here are some examples of galaxies which have a very symmetrical shape. We call them elliptical galaxies. These are some spiral galaxies, and you can see them as a disk if you manage to travel around and see them from the edge, right? But of course you can't. So these are not one objects. There's several different objects, but they look very similar. Their properties are very similar. So these spiral galaxies look alike. And then again, of course, irregulars. There's no specific shape for them. Okay. Now, these galaxies were basically, we started knowing the galaxies and we discovered them from almost 1900. I mean, maybe few decades before that we knew about them, but we call them spiral nebulae. Around 1970s, people like Besto Slipher and some other astronomers, they started measuring the velocity, the radial velocity of these galaxies. You see, Doppler effect, the same phenomena that the police officer uses to give you a ticket, speed ticket, can be used to measure the speed of these galaxies. or to check if the galaxies are moving. And so around 1970s, in the advent of spectroscopy, and Doppler effect was used significantly by astronomers to study the galaxies. Slipher used 25 galaxies and measured its velocities by measuring Doppler effect. And surprisingly, he discovered that they are all redshifted, means these objects appear to move away from us. And the velocity was pretty high, like thousands of kilometers per second. And so other astronomers tried different groups of galaxies, and eventually they were convinced that most of the galaxies are actually receding from us. There were a few examples like Andromeda galaxies and some others, which they had blue shift, means they are approaching us. The rest were redshifted. Now, at that moment, Edwin Hubble came to the picture. Around 1929, he not only measured the velocity, the recession velocity of the galaxies, he also measured the distance to the galaxies. And when he put them against each other, he realized that there's a correlation between the distance of the galaxy and the velocity, the recession velocities. The further they are, the faster they are moving away from us. And so when he calculated this rate of basically recession, he got to a number, 70 kilometers per second for every megaparsec of space. So a galaxy which is 10 megaparsec, which is about 3 million light years. If it's 10 megaparsecs away from us, then the galaxy is moving 700 kilometers per second away from us. And surprisingly, it was the same for every galaxy. And regardless of where you are, you will be able to measure that recessional velocity. This was like a universal law in the universe. Now, initially, people, of course, assumed that maybe we are at the center of the universe, but then soon we realized that this is not the case. And so the idea of recessional velocity was explained with the expansion of the space and time. So scientists were now convinced that the space and time is a stretching. The galaxies are not moving with respect to that coordinate system of the space, but because the space between them is a stretching, then the light which is traveling between them is also a stretch with that, and it shows the redshift. Now, this is useful because if now you know that the universe is expanding, you know that the galaxies are moving away from each other, you can go backward and assume that at some time they were very close to each other and estimate the age of the universe. And Hubble did that. So he estimated the Hubble constant, that rate of expansion is about 500 kilometers per second per megaparsec. And so he calculated the age of the universe to be about 2 billion years. It's funny, at the time, people knew that the planet Earth and the solar system is at least 4 billion years old. So it was embarrassing, rather. But then soon we managed to measure this Hubble constant, the rate of expansion, the rate in which galaxies are moving away from us, if you like, to a much more precise value, which is now between 67 to 73 kilometers per second per megaparsec. And using that, you can say that the universe is about maybe 13.7 billion years old. But obviously, galaxies, based on this expansion of the universe, are moving away from each other. That means a long time ago, when the universe was smaller, the galaxies were closer to each other. And also, galaxies have this tendency to form structures because of the gravity. So you have clusters of galaxies. And long time ago, these galaxies moving so fast, rapidly around each other, had a higher chance for interaction, collision. And sometimes they even merge together to form a bigger galaxy. And so the galaxy interaction allows the galaxy's shape and size to change. And the galaxy's type can also change. If they have a supermassive black hole, then after these collisions and merging, their black hole also merge together and forms a bigger black hole. And so looking through the distribution of the galaxies and measuring the mass of these black holes, astronomers realized that there is a correlation between the mass of the black holes and the mass of the galaxies. The bigger all the galaxies, the bigger is the black hole, or vice versa. I mean, indeed, we don't know which one comes first, and that's a very important question to address. Did the black holes formed initially and the galaxies are formed around them? Or did the galaxies form first and then the black holes formed maybe through stellar evolution and then accumulated more mass and grow to become a supermassive black holes? Or maybe both scenarios are happening, and in different galaxies you will have different scenarios. The only thing we know is the supermassive black holes at the center of the galaxies are usually less than 1% of the mass of the galaxies. Our Milky Way has a black hole which is about 4 million solar mass. But our Milky Way has about something around 200 to 400 billion stars, most of them similar to Sun. So it has 200 billion solar mass, but it has a black hole which is quite small, like 4 million solar mass. But anyhow, it seems that understanding the black hole can help us understand the evolution of the black holes. And these two evolutions are intertwined. We cannot understand one without the other. Which brings us to this question: how do we detect these black holes? Of course, galaxies are huge, very large, bright. You can easily detect them. But black holes are quite small, and they are quite hard to detect. Except quasars, which are galaxies with active galactic nuclei, they generate radiation. You remember I talked about these matter accreting into a black hole and forming a disk of matter called the accretion disk. Where matter tries to fall into a black hole with angular momentum, they have to lose that angular momentum to get closer and closer to the black hole. And this happens when two layers of mass within this accretion disk rub against each other. As they rub against each other, they can warm the environment, they can radiate, and they can transfer the angular momentum outward. And so the accretion disk gets warmer and warmer, and the matter rotates faster and faster as they get closer and closer to the black hole event horizon, of course. And so the temperature rises initially at quite far. The temperature is low, so they radiate. The accretion disk radiates radio and infrared. You get closer, then they radiate visible, closer, ultraviolet. And very close to event horizon, a black hole can radiate even X-ray. And so you look around the universe for X-ray sources, and then you evaluate them to see if they have some other properties of the black holes. Now, black hole accretion process is very efficient. Indeed, it's the most efficient process in generating energy. And it has an efficiency of about 10%. So if you feed a black hole at the center of a galaxy by about 1 solar mass per year, you can create a very bright active galactic nuclei, a quasars if you like, which is visible at very far distance, almost as far as 10 billion light years. Okay? And so these materials falling to the black hole will make it possible for us to see the black hole. Except there is one problem. It's a disk. And the matter far away from the black hole are cooler and cooler. Eventually, you will have a region which is like a donut, a torus of cool gas dust particles moving around the black hole. And it's obscure. It blocks your view. So if you look through the disk, you will have a lower chance to see the accretion disk or the hot regions of the accretion disk. But if you look from a different angle, you will have a good possibility to see the X-ray, for example, radiated from the inner part of an accretion disk. Cygnus X1 is an X-ray binary source in the constellation of Cygnus. This is technically the first candidate for a stellar black hole. It's a binary. You have a O star with a mass of about 20 to 40 solar masses and a black hole. And then the star is going to feed the black hole to form the accretion disk. In a normal quasar, you don't need a single star. You can have a multiple stars doing the same job. Okay, so that's one way to detect a black hole. You can also detect a black hole from radiation which comes from faraway gas. These clumps of gas which are rotating around the black hole, depending on how far away they are ionized by the radiation from the accretion disk. The accretion disk radiates significantly in ultraviolet. This ultraviolet is able to ionize the gas. And then the recombinations, which happens later, creates some radiations from these clouds. Depending on how close they are to the black hole, these emission lines will have different features. If they are very close to the black hole, then they would be very broad. If they are really far, then the emission lines would be very narrow. But eventually, you can detect these features, these broad or narrow emission lines from particularly galaxies or quasars. And so by measuring the thickness of these emission lines, you can get some idea about the mass of the black holes causing these broadening. Okay, that's also direct measurements of the mass of the black hole. You can also measure and detect the black hole through gravitational lensing. When a black hole passes in front of a galaxy or some other source of lights, like quasars, the light from the background will be distorted by a significant gravity very close to the event horizon. So you can measure the distortion and you can calculate the mass of the black hole from that distortion. That is also something we do. But for some of the galaxies that we are lucky, we can see the stars in a long observations, like tens of years. And we can see these stars are rotating around a very dark point. So this image shows you the center of our Milky Way galaxy. The observation happens for about 10 to maybe 15 years. People got Nobel Prize in 2020 for discovering this and then showing this orbit for these stars. But what happens here is because of the gravity around the black holes is stronger than the Newtonian prediction, if there is a black hole and the star gets very close to the event horizon, then its orbit will have to follow the general relativistic orbit. And so you can estimate and predict how much the mass of that black hole should be. And that is a technically direct proof of the existence of such black holes. This is how we have measured the mass of the black hole at the center of our Milky Way galaxy. And the last but not least is when two black holes are merging together, they can disturb the fabric of space and time, and they can create what is called gravitational wave. These gravitational waves are detected by large interferometric radio telescopes called LIGO, and it's direct observations of the black holes and their merging. But of course, at the end of the day, we want to see the black holes themselves, right? And so recent observations by Event Horizon Telescope, a series of multiple telescopes all around the planet Earth, created a telescope as large as the entire planet Earth itself, with a very high angular resolution. This allows us to see the black hole's event horizon and the area around it. Of course, you don't see the black hole. Remember, the black hole is dark. It does not radiate. But the accretion disk around it seen from different angle will create these shapes that you see here. So we have managed recently in 2020 and before that a little to see the black holes to some degree directly. Now, on the left, you will see the most recent one in 2024, in March 27. This is our Milky Way black holes. And in the middle, you will have M87, a 10 to the power of 10 billion solar mass black hole, which is in a very far distance, almost 1,000 times further than Milky Way from us. Now, these two images look very similar. If you look at this image of the Sagittarius A supermassive black hole and M87 black hole, they look like the same size because only these are in a different distance and different size. I mean, Sagittarius A is 1,000 times smaller than M87 supermassive black hole, but it's also 1,000 times closer to us. Now, we have a big problem observing the Sagittarius because we are in the disk of the Milky Way, and looking through the disk, seeing the center of the Milky Way, it's extremely hard. The gas and the dust within the disk prevents us from seeing the black hole. But luckily, after a very, long effort, astronomers managed to create an image of this black hole. And so with the help of these images, we can also measure the mass of the black holes by using the simulations and predicting what kind of black hole mass can create this kind of structures. Okay, so that brings us to the end of tonight's talk.
Thank you so much, Professor, for coming on tonight and telling us all about black holes and galaxies. I will now hand it over to my colleague for some questions.
Thank you so much, Professor Rafiee. I really enjoyed the talk. While listening to the talk, a question came up. So you talked about black holes evaporating, and I was wondering, I've never heard of that term before, and when I'm thinking about evaporation, I'm thinking from the perspective of how water evaporates on Earth. And I just wanted to ask you, how can I better understand when you say black holes evaporating in space?
Oh, very good question. When you think about it, it's almost the same idea. So when water evaporates, technically the water vapor escapes from your glass, right? And the same thing happens for the black holes. You see, the mass of the black hole causes the space-time around the black hole to be extremely curved and have an extreme amount of energy in it. And the quantum mechanics allows that energy to pop out of the non-existent to become matter-antimatter. Now, these particles and antiparticles then gain their energies from the black hole's mass, because the black hole mass is creating that curved space-time around the black hole. Now, if one of them escapes, or if one of them annihilates with another particle and creates light, and the light escapes, that light takes away energy, and hence the mass, from the black hole. And so the black hole is losing energy and it loses mass through this process. So Hawking predicted that if this happens, and quantum mechanics allows that to happen, then slowly this black hole loses energy by radiating these radiations. And as it loses energy, it loses mass, and it slowly gets smaller and smaller and smaller, and eventually it disappears. So almost the same process of evaporation.
That's very interesting to know. Thank you so much for explaining it.
Any other question?
Hello, Professor Rafiee. Yes, I wanted to ask, as someone who's explored the vast reaches of the universe Both theoretically and observationally, you've encountered countless mysteries and wonders. If you had the opportunity to travel to any galaxy or black hole you've studied, which would you choose and why? And what do you hope to discover during this journey?
Very interesting question. Well, the nearest supermassive black hole. Okay, so think about it this way. You see, event horizon is a very special surface. The surface gravity on the surface of the event horizon depends to the mass and radius. Okay, so when you have a small black hole, the tidal force very close to the event horizon is very huge. But when you have a supermassive black hole with the size which is about a few billion solar mass, it is so huge, it's very massive, but its event horizon is also so large. The tidal force on the surface of such supermassive black hole is so small, you don't feel anything. And so you can actually cross the event horizon without even feeling anything bad. Now, normally, if you fall to a black hole, a tiny stellar black hole, the tidal force will slowly stretches your body. And eventually, when you get close enough, you funnel into a very thin, stream of particles. Initially, you snap in half and bifurcates to 2 parts, and then 4 parts, and then 8 parts, and you break it into smaller and smaller pieces. And if eventually you become a stream of particles and you fall into a black hole, this has a very special name. They call it spaghettification. Right, you will die in this way. It's a very funny name, but the tidal force is very huge. It can affect you, can destroy you. But when you fall into a supermassive black hole, which is few billion solar masses, the surface tidal effect on the surface of the black hole is so tiny, you can easily pass through the event horizon without noticing it. And so perhaps if I have to travel to visit any of these black holes, I would like to go and fall into a supermassive black hole, which is like 10 billion solar masses. I can pass through it. If I have some astronomical devices, I can measure. And before I just cross the event horizon, I can send all the information to you. And so you can collect them and then learn about the black holes. But of course, as soon as I cross the black holes, I have no idea. There's no way to communicate with you. And indeed, what happens inside a black hole, some people have predicted, would be strange. For example, the time goes backward, and then the entire history of the universe would happen in a second for you. Everything would change color. So I really like to know it firsthand. I mean, so if I have to go somewhere, I guess I would just go fall into M87 supermassive black hole.
Thank you, Professor.
Any other question?
Thank you again, Professor, for your beautiful speech. I heard that Andromeda and Milky Way galaxies have started merging. Do you think that is true? What would be the consequences and the duration of the changes?
That's a very good question. Yeah, especially that I said the universe is expanding and the galaxies are moving away from each other. Then what's up with this Andromeda galaxy, right? Well, galaxies have a tendency to form structures, and galaxies within a structure have a chance to interact with each other and maybe even collide. And so it's true, Andromeda galaxy is moving toward us with some like 300 kilometers per second speed. So it is 2.5 million light years away from us, but it's traveling quite fast. So if you wait another maybe 2-3 billion years, Andromeda galaxy will reach us. Now, initially, we're not in a head-on collision. Initially, we will encounter a close encounter. Andromeda galaxy and Milky Way will spiral around each other, and eventually they merge together. Andromeda has also a supermassive black hole, so it would be interesting to see what happens when 2 supermassive black holes merging together, we should have very interesting gravitational waves, so we can measure that perhaps. But interestingly, during that period, which is quite long, billions of years, you can see a lot of stars in the skies. The gas will merge together, form new stars. Stars may actually not collide with each other, but they pass by each other's and they may disturb each other and distort each other. But definitely you will see a lot of stars in the sky, much more dense night sky. So if you are an amateur astronomer, I recommend you to stay around another 4, maybe billion years and definitely see the moment where these two galaxies are close by and then they merge together. You will have an amazing sky. But of course, you have to be extremely patient, 4 billion years maybe.
Thanks so much, Professor. I wish I could live that long to see how the collision would have happened. Thanks again. Then I would give to Maheen then. Thanks so much again, Professor.
Thank you.
Well, everyone, you have been listening to the Allen I. Carswell Observatory's monthly Teletube broadcast, the Astronomy and Astrophysics program, written and presented by the students, faculty, alumni, and friends of York University. A special thanks to Professor Rafiee for an amazing talk tonight. The hosts this evening have been Zena, Pouria, Noor, and myself, Maheen. All of our programs are free, but if you would like to make a donation, see our website at yorku.ca/science/observatory. You can always connect with us on Twitter with the handle at York Observatory and check out our website for show notes, content, updates, and contact info at yorku.ca/science/observatory. Thanks for tuning in. Clear skies and have a good night.